Hello, students. How are we doing today? Well, my name is William Ollis. My students call me Professor Ron, and this is going to be our Calculus 2 class. And what I want to do is, again, remind you to make sure that you have a workable Sanjak ID with your, a workable Sanjak email. When I do conference hours, I'll have to send an invitation to all of my students. So I need a workable email for each one so I can include that list in the recipient list in Outlook. So if you already use your Sanjak email, then you're fine and you don't have to worry about it. But if you're new or you've never activated your Sanjak email, please do that so I can include you on the list. Now what I want to do is go ahead and share my screen. And first, what I want to do is get a warm-up done. And in this particular case, I want to do a fairly straightforward one that you would have done in pre-calculus. Let's see here. Now what we have, what I'm going to call this is just a warm-up. Now there are instructions to all of the ideas that we need to do to get prepared with WebAssign, and I'll say more about that. And here's what I want you to do. This is a pre-calculus problem. And if you look at the first practice test in Calculus 2 in your Blackboard site, you'll see this problem. So we want to write an algebraic expression. Sometimes I'll type, but I'll write for now. Write an algebraic expression for the following composition. And here it is. This is sine of 2 times the inverse tangent. Now, there are going to be two expressions for inverse functions in WebAssign. Sometimes they'll say arctan, and sometimes it'll be tan to the superscript -1. I'm going to use the -1, and WebAssign's not going to care. But if you prefer the arc, that will be fine too. Let me turn down my email notification. Now, does this look familiar to anyone? Here's the first thing we want to do is assign, that is, let u be the inverse part. That is, let u be inverse tangent of 3x. And you notice this is a double angle formula, so we're going to have to use that too. Now, what does this mean? Now, I'm going to go through all of this information when we derive some formulas for the inverse trig functions, but I just wanted to do a pre-cal problem that hopefully will make you feel comfortable. So now we're going to apply tangent to both sides. So tangent of u will just equal 3x. Now, remember from pre-cal that the u, the inverse tangent, lives between -pi/2. Remember when you drew your inverse trig functions and believed your professor? So actually, this is the u here. Let me use my eraser. Oh, I've got to go up here, and I like the note. It's a little bit easier, but this will be fine. So we have a u here. Notation's important, obviously. And also we have the identity. Let me remind you of that. Sine of 2u equals, this is what you learned in trig, 2 sine u cosine u. Okay, so now we need to fill that in. So what does this imply? So this implies sine, we'll just go back to the original problem, of 2 inverse tangent of 3x. And now I'll go ahead and replace with the u is just, oh, and of course here, sorry about that. There's a u in there. I'm sure you all saw that. This will be 2 sine u cosine u. I've got a document camera coming from Japan. That was the only place I could find one, so I will use that too. It certainly makes it easier to write than using the tablet. Now, so we need to just figure out what these particular expressions are. So note, let's go back here. And if you like, you can draw a triangle. I'll do it 2 ways. Since everybody likes triangles, we'll just go ahead and do that. So we have tangent of u is 3x divided by 1. So we can draw a triangle, a right triangle. Again, triangles are fine because they're easy. We can just use the Pythagorean identities to fill everything in. So now we have a u here. And then the tangent is opposite over adjacent. So this will be 3x, and this will be 1. Now, of course, by the Pythagorean theorem, the hypotenuse will be the square root of the sum of these guys squared. So let's go ahead and write that in. Square root 1 squared is 1, plus 3x squared is 9x squared. And you can just extend that radical there. So that gives us a way to write the other expressions. So now if we need sine u, so what does this imply? So hopefully this is coming back to you now. Sine u will just be what? Opposite over hypotenuse. So we'll just say sine u. I'm just going to flesh this out a lot because I know everybody's pretty rusty, but we will use these techniques a lot. This will be 3x divided by the radical and then of course the cosine of u will just be adjacent over hypotenuse. So that will be 1 divided by the square root of 1 plus 9x squared. Now, again, you can do these all with the Pythagorean identities, but I know you like the triangles, so we'll focus on that. Now we can just put this all together. So to close, this will imply, we just multiply things. Now, of course, what you're seeing here is that the cosine term is always positive. And that makes sense because if you look here, right here, that's where the cosine is actually positive if you think about the unit circle. Now, of course, the sine function can change. The x will determine the sign here. But of course, if we think about this, u being between 0 and pi over 2, this will be positive. And then, of course, u being between negative pi over 2 and 0, this will be negative. So the sign of this is carried correctly for the sign of u. So we don't have to worry about that. Everything worked out really well. So now we can say sine of 2 inverse tangent of 3x will now be, and let's just fill everything in. We have our 2 So I'm going to just say 2 times the sine u, that's going to give us a 6. So I'll just write 6x divided by the square root. Writing on the tablet certainly makes me go slower, so you'll probably be very grateful for that. And then, of course, the cosine is 1 divided by 1 plus 9x squared. And now when we multiply, we just use the laws of exponents, and we get 6x. And of course, we have 1/2 plus 1/2, giving us 1. So the denominator becomes 1 plus 9x squared. And I usually end my problems with 2 little slashes there. That just means we're done. Now, what I want you to get out of this is just basically a review of some of the aspects you talked about in pre-cal when you dealt with the inverse trig functions. Again, we're not interested in everything being perfect, but we want to be able to look at things in terms of an inverse trig function with a right triangle. So let's look at another page here. So now that we have a warm-up, now what we want to do is consider, I'll go ahead and type a little bit here. So let's just say this. We now look for formulas to represent the derivatives of the inverse trig functions. Now, and I'm going to use trig for trigonometric just to be lazy. And you're going to think, does that mean we have to do all 6? We're going to focus on 3 of them because the signs between the inverse cosine and inverse sine derivatives differ by a negative sign. So we don't need to repeat ourselves. So we will focus on inverse sine, inverse tangent, and inverse secant. Now, if you studied Calculus 1 at San Jac, you may have talked about some inverse hyperbolic functions. When I teach that particular class, I do some work with the inverse. And so you can do calculus in many different ways. When we start doing integrals and things, don't worry that sometimes your answers may look different. It just really depends on which formulation you use. So let's do the very first one. So we got started with our warm-up, so now this won't seem so odd, hopefully. So we're going to say, we're going to use some implicit differentiation, which is basically the inverse function theorem. When you look in your lecture notes for this section, my handwritten notes, and also when you look in the PowerPoints, usually there's a focus on implicit differentiation. The inverse function theorem is fine, and it's your choice. Either way is good. So just say we have y is equal to the inverse sine of x. So that's like we're back in pre-cal, and we remember we just used this idea. If and only if x, apply sine to both sides, equals sine of y. Now, does anybody remember, kind of like the tangent function, where do the x's and the y's live? Let's go ahead and write that down. If and only if. When you used your, they call them cancellation rules. I don't really use the word cancel, I say absorb. But for those to be correct, we had to have the following. X lives, again, this will be the flip of what you anticipate, -1 and 1. And then y will live between -pi/2 and pi/2. So when we construct the inverse sine function, remember, we restrict the domain so that we can produce a one-to-one function. And you know that one-to-one functions are invertible. So again, you might think this is a little bit just like, okay, well, we just decided to define this function this way. Well, it's become convention. So when we think about the inverse sine and the inverse tangent, those definitions are universal. The only thing that we have to worry about sometimes is that the definition for the inverse secant is not universal. And so we have to be careful that we always keep the definition in mind that a particular math book or particular problem is using. Now, what we want to do now, and let me just go ahead and do some text. I tell you, these tablets, you hit the little shortcut keys and you're in trouble. So we'll say we differentiate implicitly. I want you to see where these functions come from, these formulas. That way this will make it a lot easier, and you won't think we're just making this up. So now focus on the easy equation. See, when we talk about these functions, we want to say, well, let's go ahead and differentiate something we understand. We don't know the derivative of the inverse sine function, so we can focus on this. Now, when I say differentiate implicitly with respect to x, so the derivative of x with respect to x is just 1. We like that. That was the first part of calculus 1 that was easy. And then y is assumed to be a differentiable function of x. So the derivative of sine is cosine. Again, another calculus 1 result. And then by implicit dy dx, or you can use y prime. I prefer the y prime, but since we're doing a formal derivation here, let's go ahead and use this. Now, again, remember, differentiation with respect to x derived by x, just 1. The derivative of sine y will be cosine y dy dx. Now, this is what we want. Notice dy dx is actually the derivative of the inverse sine function. So we want to solve for that. And then we're going to use our little trigonometry tricks, which is what we did in the warm-up. So we have dy dx. I like to start with the inverse sine because it's pretty straightforward and it's pretty simple. So now we want to divide both sides by cosine y. So what we're seeing here is that we know that cosine y would be 0 at negative pi over 2 and pi over 2. So we're going to have to kind of kick those out. So this will only make sense if we don't let y be pi over 2 or negative pi over 2. So we get our cosine y right here. And this will just mean that y lives between negative pi over 2 and pi over 2. That means the x is going to live obviously between negative 1 and 1, so we're going to kick that out. But that comes in a little bit. Okay? Now, what we want to do is, this is a nice formula. It's a true formula, but it's not very useful for us in this form, because notice here our independent variable is x. So what we want to do is introduce the independent variable x by using Pythagorean identities. Now notice, like we had before, the cosine will live, the y lives here, and this is where the cosine is positive. So we're going to rewrite the cosine as the square root of 1 minus sine squared y. So now this will just say equals, I'll just continue this on, 1 over the square root, just using our fundamental identity, 1 minus sine squared y. I thought about this and I thought this is so much easier than trying other methods, because this is appealing to what you already know. So again, the cosine y is positive for these values of y. So we simply replace it with the square root, positive square root of 1 minus sine squared y. Now notice when we go up here, we see that sine y is just x. So this gives us 1 divided by the square root of 1 minus x squared. Now this formula is a lot better. So now we see that the actual derivative of the inverse sine relative to x is 1 divided by the square root of 1 minus x squared. That's a good formula. So that solves that. So just to recap, let's just go ahead and say, what does this equal? Well, dy dx, let's go ahead and fill in y. This is just the x derivative of the inverse sine function. Now, what you're seeing here, ladies and gentlemen, is that we start with a transcendental function and we end up finding that its derivative is algebraic. And notice this appeals to what you already know. This is an even function from your pre-cal. We got the x squared here, so this is always positive. And that makes perfect sense because we know that a derivative that's always positive denotes an invertible function, which this is. So we have this nice little formula here, which of course is good, but it's not very user-friendly. So we'll extend it because that's what we do in calculus. We like the chain rule. So we want to do a chain rule extension. So let's do that. So let's start here and we'll go up and get some text here. Let's just do a little text box. So here we extend, and this is what we always do in calculus. You're used to this. We extend this formula for Monday typing formula by the chain rule. So suppose, and we like to use u, suppose u is a differentiable function of x. So what we're seeing now is that, okay, this is going to pave for a much more generalized formula. So now what does this imply? So this implies that now if we take, and of course with every derivative formula, we get a nice integral formula. If we have the x derivative of the inverse sine of u, and of course u is a differentiable function of x, like maybe 3x or the square root of x squared plus 1, some differentiable function of x. This will now equal, just replace the x with the u and then tack on the du dx with the chain rule. So this will be 1 divided by the square root of 1 minus u squared du dx. So there's one thing that students always forget. They always forget the derivative of the inner function. And that's easy to do. We all do it. But just know now that if we are taking the derivative of the inverse sine where the argument is something besides x, we have to tack on the du dx. So this gives us a nice extended formula. And you'll see all of this in your ebook with your WebAssign. You'll really like WebAssign. It's great problems, keeps you busy. You know, you'll do your 5.7 and 5.8 this week and do your quiz 1, and I've already got those due dates up for you. So you'll like that. Now, what I want to do first before we move on, for instance, let's just look at a simple example. I've got an example here that we can just go ahead and apply this. And then what we want to do is write down a user-friendly integral formula that we get from this. So here's an example. And this is actually, I believe, a test example. So we'll say example here. Now you're going to find that these formulas are pretty easy. So we have y. We just have to remember that they're, a little bit unusual, but we'll get used to them. Inverse sine. Now again, you can write arc sine, or you can write sine superscript -1. I like this notation, but the arc sine you'll see used in WebAssign, so you can use whichever you like. It won't matter. WebAssign will take either. So say we have the inverse sine of 12x plus 9 divided by 5. And we want to compute y prime. So one nice thing about calculus, you remember when all you had to do was compute derivatives, it was easy. And then when you had to start doing word problems and integrals, it got hard, because you had to think about what you're doing. But at least with the derivatives, it's very straightforward. So now what we can do, and let's just kind of break this down a little bit. We notice here that the u is 12x plus 9. Again, I'm doing a lot more steps now because I know you're rusty. I'm sure you haven't been studying math all summer, or maybe you have. I had a 5-week Calculus 3 course and a 5-week pre-cal course, so I did have some students that did a lot of math. And now, of course, this is a real simple derivative. We can go ahead and write this down. Du dx will just be what? 12 over 5, because the 9/5 is a constant. So we can just go ahead and write this down. Now, you don't have to do this. I'm just adding a few steps here to make everybody a little bit more comfortable with the notation. So we have 12/5 there. Now we can go ahead and apply the formula. So this implies, so if and only if, y prime will equal, now what we do, remember the formula, we have 1, and we have to square the u. So I'm going to use brackets here for now. The square root symbols are kind of hard to write. So we have 1 minus, now we're going to have u squared. So we'll go ahead and square it. Well, I'll just write it out for now, and then I won't skip steps. Sometimes the steps are obvious, but again, let's just go ahead and put in all the steps right now. Later on, we'll have to leave out some as we get more knowledgeable of the information. So we have the square root here, and I'll just use the 1/2 power. So remember, this is 1 divided by the square root of 1 minus u squared, and then times the du dx, which is 12 over 5. Now, this is fairly simple algebra, but again, I just want you to be careful with it. Sometimes, like I say, we won't do as many steps. Now, notice here, when we square this out, we're going to have a 25 downstairs. So we can go ahead and get a common denominator. So we're going to have a 25 as a common denominator. I'm writing kind of large here. And this will be, of course, 25. We won't worry about expanding that binomial. That's not really going to help us out much. If you want to, you can, but I don't think it's necessary. It's not going to move the problem forward. So we'll have 12x plus 9 quantity squared. One half, and then times 12 over 15. Excuse me, 12 over 5. We don't need 15, Professor Ron. Okay, now notice when we do the square root here, that's just going to be 1 divided by 1/5. And so the reciprocal of the reciprocal is just the number. So this gives us 5. That comes upstairs, 5. And now we can go ahead and write, we'll go ahead and do brackets until we get to the end, and we'll write the radical symbol. So that's a minus. So we have 12x plus 9 quantity squared to the 1/2 And then of course times the 12 fifths. You know, when you do calculus problems, you do a lot of bookkeeping, but that's okay. Bookkeeping is good. Notice the fives absorb. Instead of saying cancel, I'll usually say absorb, and that'll clean it up nicely. So this will just give us 12. And I don't use slash lines. I don't really like to see slash lines in your work because they cover up the work. Notice these absorb or cancel. And that just leaves us with, I'll go ahead and do the radical, but first I'll write the radicand and then put the radical on it. So we have 25 minus 12x plus 9 quantity squared, and then we can put on the radical. And so now, again, this was an old test question. If you look at some of the practice tests, I've just uploaded some old tests from last fall. Again, the calculus problems, ladies and gentlemen, don't change. They're the same over and over and over. Calculus has been around for over 300 years. And so it's not changed, but it is a useful and just profound academic part of our lives. I mean, it covers everything that we do. And so when we're long gone, our friends and our colleagues will still be doing calculus to solve their math problems. Now what we want to do is go ahead and see what we can do for an integral formula. So here's what we want to do. Note, just from what we have, we get a really simple formula. That is, if we just integrate the derivative formula, we get the following. Again, we want to make this more user-friendly. So this would say du square root 1 minus u squared. So, you know, we could have 1 and bring the du out here. It doesn't matter, but this is a more compact form. So if we just basically undo the derivative formula that we found using the chain rule extension, we just get this. And then, of course, we have to tack on the arbitrary constant. We know from the mean value theorem that functions that have the same derivative must differ by a constant. So if we were looking at the derivative formula, it would automatically say that the integral of 1 minus u squared du, or excuse me, 1 minus u squared square root in the denominator du is equal to the inverse sine of u plus an arbitrary constant. So that's a formula, but we can make it more user-friendly. And here's what we're going to do. Now we're going to let a be a positive number. Again, I'm a be positive. I got a little, sometimes on these tablets, sorry, got greater than 0. We're going to make this positive with in this case, u divided by a less than 1 in absolute value. So what we want to do is note that u here would, in absolute value, would have to be less than 1. Now, if we want to make a user-friendly formula with a positive a, then we need to have this stipulation so the formula makes sense. So now this implies we replace, that is, replace u with u over a. And you're thinking, why do they do this? Well, ladies and gentlemen, this has become convention. This is just how it works when you have to consider the fact that many mathematicians and physicists have come before us and they've developed these nice formulas. So now we get the following. That is, we have the derivative or the differential of u over a. So this is why we did the last problem, so we get some practice with some algebra. And I'll use the brackets here. So we get 1, and go ahead and square it out, u squared divided by a squared, 1/2. So we're going to work on this side, and then of course it's going to be equal to this, and we'll put that in as we need it once we work this down a little bit. Now, the differential here, again, is going to be easy. That we have the constant 1/a, so that's just going to come outside. We can go ahead and pull it out. That's going to be 1/a. And this will be du. And then, of course, now, just like we did before, we're going to get a common denominator of a squared. So this is mirroring the last problem. That's why I did it, so you would already know the algebra. So this is a squared minus u squared divided by a squared to the 1/2. Use the brackets. I mean, the radical signs are hard to write, and this works out fine. And so now, remember, just like we had the problem before, where we have the square root of 25, that was 1/1/5. So this is going to give us 1/1/a. Remember, the square root of the a squared is the absolute value of a, but we have assumed that a is positive. So this is just going to give us an a/a. So basically, we have a/a integral du, so that the a's are going to absorb. And students always get bothered by that, because in the other formulas they don't, and they always forget this, but that's what makes this formula easy. So that's the a's absorb, so we just get the integral of du square root a squared minus u squared. And of course, now on the right-hand side, we just replace the u with u/a, and we're done. So this turned out to be pretty easy. But again, all this work to make it more user-friendly extends the use of the formula. And you physics people, which most of you are because you want to be engineers, you'll see this formula all the time. So now we have a basic integral formula, and this is a basic integral formula from the list. If you use your Larson text, this will be towards the bottom in the 20 basic formulas. So now what we see is that we have a Pythagorean integral. That is the integral of du divided by the square root of a squared minus u squared. It's just the inverse sine of u/a plus a constant. So that's a beautiful formula. Again, that's easy to work with now. Now notice what we need to see from this. This is a form, okay? And so when we work problems, we notice that we have certain forms with integrals, and we make the problem fit a particular form, or we actually manipulate it algebraically so it fits a form. We can't just change it up. I mean, we have to do it legally, of course. And so that's why we know that integration is so much harder, because we've got to have some formula that makes sense. So let's just go ahead and use this in a simple problem. We can be real creative with this, but now let's just go ahead and do an example of this, a very simple problem. Normally I like to get out all the formulas, but now that we're online, we might as well make the process a little bit easier. So let's look at a simple example. This again is like a WebAssign problem. So let's look at this one. Say we have a definite integral, 0 to 1, and this is really simple, but a very useful example. Don't be afraid to use your algebra. Don't be afraid to go out on a limb, because in Cal 1 and especially Calculus 2, we have to always manipulate things algebraically. And like I say, with this class, study it every day. Calculus is hard. And so in order to have some success, you have to really be consistent and stay up with your routines. Now, when you look at this, you say, well, Professor Ron, this is an easy problem. The u is just x, and we've got an a squared here, so we can just say a equals 4. That is 4 squared is 16, and the u is just x. Well, and du dx would just be 1. So we like that. That's easy. So now just to be a little bit more straightforward with this, let's just go ahead and write this with the square downstairs. So you can see that this exactly fits the inverse sine form. So we have, I'll go ahead and write the 4 squared first. A lot of times when you're using the tablets, do this first and then do your square roots, or even writing on a whiteboard, which is basically what this is. So now when you look at this, everything's set up for the integral formula of the inverse sine. And so now we just fill it in. So we know this is inverse sine, and we don't have to put in the c. Of course, that's just going to absorb it. We'll subtract out. We just have u over a. So this will be x over 4. Now, of course, if we had no limits of integration, we'd be done. We just tack on a c. And now we do our vertical line because we're lazy. The calculus notation really has evolved. This was not done this way initially. All the smart people that came after Newton and Leibniz developed these notations. So now by the fundamental theorem, we simply fill in. So this will be inverse sine. This is where we use our pre-cal. Now, of course, if I replace x with 1, I get 1/4. Now, that's not a standard value from the unit circle, so you leave it alone. Let me make a point here. When you do your WebAssign, if this is what you get, then that's the answer. Students tend to get very confused, and there should be no confusion. If WebAssign does not say approximate to some decimal place or to the nearest whole number or whatever, you are to give an exact answer, always. I had students be very confounded by that, and I'm not really sure why, because when you do a math problem, you give an exact answer. So unless the problem says approximate, you give an exact answer and use all the nice little tools and symbols that WebAssign provides for you. So we leave that alone. And then, of course, if we replace x with 0, we just get inverse sine of 0. And we know what that is. That's just 0. So we're using our pre-cal. So now, of course, the inverse sine of 0 is 0, and the inverse sine of 1/4, well, that's not a number that we know. That never terminates, so we're just going to write it exactly. So inverse sine of 1/4. Now, I don't use a lot of parentheses, ladies and gentlemen. WebAssign will put them in, but when it's very clear that we're doing the inverse sine of 1/4, I'll leave it as that. When you start doing sums and differences and all, you need parentheses, but here it's very clear. It's unambiguous, so to speak. So now what we see is we can do this very straightforward integral. Now it's straightforward, just using the inverse sine form integration that we've just derived. Okay, so again, when it comes to doing problems of this nature, what's important and what you're going to find is you're simply looking for patterns. The more patterns we see, the easier the problems are to do. And here's another thing. If you come up against a problem that you can't do, for instance, because you don't have a form that it fits, then that's okay. You may have to take a second look to say, well, maybe I've missed something. Maybe if I manipulate this, I can make it into a form that I do understand. But don't worry that you may see a problem in an engineering class and a science class that doesn't fit one of the forms we've done so far. So don't worry about that. I mean, don't make it up. Now, let's go ahead and look at the next formula. This is going to be the inverse tangent. And students enjoy the inverse tangent. A lot of you will go on to do engineering math, differential equations with my colleague Nate. You will do probability. A lot of you in engineering fields and even math and computer science will take probability, and you'll see this integral a lot. So what we're going to do now is say y equals, and develop a formula for the inverse derivative of the inverse tangent. We're going to say y is equal to inverse tangent of x. So now you can tell me how to do this problem because it'll be very simple. So we're interested in finding dy dx. So now what we see is that y equal dy dx, y equal the inverse tangent of x is equivalent to, and go ahead and take tangent of both sides. Again, the tangent of the inverse tangent just gives us x, as long as x lives in the right place. But with the inverse tangent, it's very, very flexible. So again, using a little bit of pre-cal. Now, what do we remember from our pre-cal work? We know that x is just a real number, so that's very flexible. We're thinking about the principal branch of the tangent function. It has the vertical asymptotes at negative pi over 2 and pi over 2. And then, of course, the other caveat is that y lives between now two horizontal asymptotes. That is negative pi over 2 and pi over 2. So in the inverse function, the vertical asymptotes become horizontal asymptotes, which is something you learned about in pre-calculus. Your pre-calculus course, you probably found to be just as hard as Cal 1. There's so much good information in that class that we use over and over. Now what we want to do is the same thing that we did before. We differentiate implicitly. So let's just go ahead, I'll remind you of that. So what we will do is differentiate implicitly. So now what we can see, this, like I said before, you all are the experts now. So we look at the equation that we know something about. So the derivative of x with respect to x is 1. And now the derivative of tangent, remember that's the secant squared. So we have to know Cal 1 to do Cal 2. You're thinking you could have done these problems in Cal 1, but you do inverse hyperbolic instead. Well, that's what I teach. And then, of course, dy dx. So now we're saying, okay, well, the dy dx is what we want. This is what we're seeking a formula to describe. So now what we want to do, if and only if. Now notice, we're staying away from negative pi over 2 and pi over 2. So when we divide by secant square, we don't have any problem with that. So dy dx, again, this is why we did the warm up, so we can get back into our right triangles. So dy dx will just be 1 over secant squared. Now, again, this is a correct formula, but it's not relative to the independent variable x. So we're going to use the same trick we did before. Remember the Pythagorean identity, 1 plus tangent squared equals secant squared. So we're just going to replace, and you're thinking, well, there's no radical in this problem. So it makes this form a lot easier. We'll just now replace secant squared with 1 plus tangent squared. Now, when you go back through this, and you can look in the lecture notes, I've used the inverse function theorem, but it's the same process. You do the same algebra over and over. Now, again, this is much better. We still have a y, but when we go back over here, we see that x is actually tangent y. So tangent squared y is x squared. And this is a very, very famous formula. So now we see, and I'll go ahead and write this in. this will give us the derivative with respect to x of the inverse tangent. So here's a formula like we had before, but it is not terribly user-friendly. Just like with before, we want to extend this by the chain rule. So I'll just write here, we'll just go ahead and do some text. So suppose u is a differentiable function of x. And of course, u, it has no restrictions. It's replacing x. So suppose u is a differentiable function of x. So now, by the chain rule, we have so what that's going to give us? Well, for instance, let's go ahead and replace x with u. So we have the derivative with respect to x of inverse tangent of u will now just be 1 over 1 plus u squared times du dx. Now, before I didn't go ahead and extend this like I did with the inverse sine. I just went ahead and did a derivative problem. But let's just kind of remind ourselves that this is exactly what we did before. This is more user friendly, and it gives us an integral formula. And you think, are we going to do the same thing we did to the other one? Absolutely. We're going to extend it, make it more user friendly. So the idea here is we can see that this formula is algebraically simpler than the inverse sine derivative because there's no radical. Now I have a web problem here that I want to look at. And this is from your WebAssign. So a lot of times when you do your WebAssign, you'll say, oh, Professor Ron did that problem. But of course, the WebAssign may generate some different numbers. But the techniques that I'm giving you will help you do these problems. The idea is I want you to practice and I want you to develop a comfort, a sense of ease with these problems. By doing them a lot, you can do your work very, very quickly and very efficiently. And I'm not even worried that you work quickly. That doesn't matter. I just want you to work with understanding. So now let's look at an example here. We're going to need a little bit more space. So we've got the following, and we're going to use some of our log identities. So we're going to have y equals, here's a web problem. We have 9/2. Again, WebAssign likes to throw in numbers just to trip you up. Dr. Larson, Ron Larson, wrote this book, and he is a topologist, and his calculus book has become one of the most used, widely used calculus books in the country. So we have natural log of x plus 1 divided by x minus 1. So we get to review some calculus of the natural log, which we enjoyed in Cal 1. Plus, now of course you're thinking, Professor Ron, you're going to put an inverse tangent in here, aren't you? And we do. Now this doesn't really involve the chain rule so much, but it does give you a new idea on how you can now combine the calculus of functions that you learned about in Calculus 1 with the new functions that you have in Calculus 2. So let's do this. Let's compute y prime. Now, first, remember back in Calculus 1, you used the log identities to simplify the logarithm so you wouldn't have to work so hard. So before we do this problem or continue with it, let's just go ahead and reduce it a little. Now, this 9/2 we can just keep outside. I'm not gonna have it straggling around. We're just kind of, I'm thinking what we can do. Well, I guess we can go ahead and multiply and just multiply through. That might be easier than having it outside and having to do parentheses every time. So I'm going to have 9/2 times 1/2. And then what I'm going to do is I'm going to write the log of a quotient is the difference of logs. So this will be log of x plus 1. Now, of course, I need parentheses here because that's a sum. That wouldn't make sense otherwise. Minus natural log of x minus 1. Now, if you will, let's just go ahead and multiply the 9/2 times the inverse tangent. Okay, so now what we're seeing is we've got 9/4 times the difference of two logs, and then we've got 9/2 times the inverse tangent. And we know how to differentiate all of those. So this implies that y prime, of course, this will just be 9/4, good old arithmetic. Now, if we look at this, remember, we have the reciprocal. Differentiating the logarithm, we take the reciprocal of the argument and multiply by its derivative. Again, it's 1 in both cases. So we just get 1 divided by x plus 1. You're thinking, well, we have to do more algebra, but it's still easier. And then, of course, the reciprocal of x minus 1 is 1 over x minus 1, and that derivative is again 1. So 1 divided by x minus 1. And of course, we'll want to get a common denominator to make this all look nice. Now, of course, the derivative of the inverse tangent, remember the 9/2 is just a constant, so we just keep that to the left. And this will be what? This will just be 1 divided by 1 plus x squared. Okay, so that's a derivative. And there's nothing wrong with this. I mean, if you're doing a WebAssign problem, they don't always care about how much you simplify things unless they make some specific formatting request. You don't have to worry as long as what you produce is a valid mathematical response. Again, remember, everything is exact unless otherwise requested. Now, this is true, but say we're doing a problem, a word problem, we need to analyze the derivative a little more. We want to clean this up some. So let's go ahead and do some algebra on it. Maybe we're writing a textbook and we're filling out a solutions manual. So now what we want is a common denominator. So this will be x plus 1 times x minus 1. That's just a difference of 2 squares, right? That's x squared minus 1. So that's the common denominator. Now, of course, we need an x minus 1 here because that's not in the denominator of the first term, x minus 1. And then, of course, we have the minus that comes along for the ride. And then, of course, here we don't have the x plus 1, so we do x plus 1. Oh, I'm sorry, let's see here. It looks good. Eyes are playing tricks on me. Now plus, and this will just be 9/2. Won't do anything to this yet until we combine them. I think that'll be the easiest. So now what do we get? So we have 9/4. Now notice the x minus the x, they absorb, but we have a -1 minus a 1, so that's a -2. And then of course we have plus 9/2 times 1. And I'm going to write the x squared first because that's going to make it a little easier to get a common denominator. Again, we're going to have another difference of squares. Now, if you will, notice the 2 here will absorb right there. So that's going to give us a 9/2 on both sides. So we'll just say 9/2. Now, of course, when we get the common denominator, this is x squared minus 1 times x squared plus 1. That's a difference of squares. That's just x to the 4th minus 1. And now we'll fill in everything, remembering the minus here. Here, that's just a minus. So this is, when we absorb here, we're left with a minus 1. So that we'll get the common denominator. This will be a minus x squared minus 1. Then we have plus, and of course we need this factor over here, x squared minus 1. Just some simple algebra, not difficult. I mean, it looks hard, but of course it's not. It's very simple. You could tutor your friends who struggle in algebra. So now notice the x squared terms absorb, and we have 9. Of course, and I'll go ahead and write this out, 2. And then we have a negative 2. X to the 4th minus 1. Sometimes in calculus 1 and pre-calculus, you spend more time doing simplifications than the actual process, but the simplification is important, especially in engineering, mathematics, and physics. So now the 2's absorb, and we have a negative. And a lot of times students will say, well, can't we just leave it this way? Sure, but then of course we can absorb the negative by multiplying and dividing by -1. So at this point, if you want to get rid of that negative, multiply and divide by -1. That'll give you a 9 divided by 1 minus x to the 4th. And that looks to be a nice answer. So what we're seeing here is that when you look at this part here, this is the derivative at this point, but it does now offer many ways to analyze this. That is, this particular derivative here now can be easily analyzed just using your techniques from college algebra. So again, we'll just say this, and I'll do a little text here. So we'll see this is to be the case. Algebraic simplification is necessary if we want to analyze the derivative. It's like when you're doing the max-min problems, the optimization problems in Calculus 1, if you're looking for critical numbers, then you really do have to manipulate the equations so that you can solve them. Otherwise, again, the analysis would be next to impossible. Okay, so now let's just go ahead and get a user-friendly integral formula, and then we'll work on a formula for the inverse secant. I want you to be able to know where these formulas come from, and then I want you to practice, and then when you're tired, practice some more. Now, everybody's on mute. So far, if you want to unmute yourself, if you have a question, you certainly can ask. I know that I tend to go on forever and ever, but I'm trying to go slowly enough so that hopefully the ideas make sense. So now we see that with the next calculation, we want to make the integral of the inverse tangent more user-friendly. So let's do that. So we know if we integrate the derivative form, we get the derivative of du divided by 1 plus u squared. And you're thinking, why, Professor Ron, do you put the 1 first? You know, usually we do u squared plus 1. Ladies and gentlemen, that's just convention. You see it written that way and you get used to it, but it does not matter. It does not matter. Note that by integrating the derivative form, this is just the inverse tangent of u plus a constant. So even if you did this with the inverse hyperbolic, it's the same routine. What we notice about the standard trig functions is that we define them via a unit circle. So we do not have formulas for them. We have to manipulate these formulas based upon their identities. So this is very, very unusual. We're used to having formulas. When you define the trig functions, that's an abstraction, very much an abstraction. So you should really appreciate the fact that we even have these formulas. This is really important. So now, like we had before, suppose A is a positive number. Nice thing about the tablet, you go slow enough so you hopefully don't make a million mistakes. Now, what we want to do is replace u with u over a, and it can be any real number, so that's not a problem. So let's go ahead and do that. So let's replace u with u over a. And so what we're going to do is operate on the left-hand side, and then if we have any stuff to multiply, we will, just like we did with the last one. Okay? So again, keep your thinking caps on. So this will be the integral. What I tried to do was think about a very straightforward way to do this so it would be user-friendly. I know we have a different set of circumstances, but we still have the same level of rigor. And to be completely honest with you, just remember the fact that as we have challenges in life, that the working through these challenges makes us very strong and makes us better. So we have to almost reinvent ourselves. My grandfather always said the necessity is the mother of invention. That is we are required to have certain things in place in our lives. We have to invent things. We have to really search deeply to figure out ways to do things. So just remember that when you're working at home. So now we have 1 plus u squared divided by a squared. Now again, the differential of u over a is just 1 over a times du, the a being a constant. So we can go ahead and factor. So let's do this. Notice this is going to be a lot easier than the other problems. No radicals make our lives easier. I think the worst thing about algebra is when you start talking about nth roots and then everybody checks out because it is more complicated. So let's get a common denominator. So we have a squared plus u squared. That's why I've been doing a lot of algebra in the derivative problems, so you get used to the algebra. It's not to make you seasick, it's just to help you out. Now, of course, notice with here, we have 1 over a squared. So that's just going to give us a squared. And of course, we can factor that. So that's going to be a squared divided by a times the integral du a squared plus u squared. Now, of course, the a squared over a reduces to a. So we have a times the integral du. You know, when you see these calculations done, you really understand that we're just doing a lot of college algebra, and that's really what pushes us forward. So the techniques that you learned in college algebra and pre-cal are so important. Now, of course, we have the a, and notice this equals the inverse tangent Now what I'm going to do is I'm going to replace the u with u over a, and then I'm going to write my constant as just C1. I know that's kind of cheesy, but I'm just saying we'll call it C1 because we always like to write the final constant as a C. So say we just call it C1. Now we need to divide by A. So if and only if, or multiply by the reciprocal of A. So we get du A squared plus u squared. And this gives us 1 over a. That's where the 1 over a is that we didn't see with the inverse sine form. And then, of course, we have plus 1 over a times the C1. Now, what we get from this is that now we can just write the 1 over a times the C1 as a constant. Just multiplying 1 over a times an arbitrary constant is just arbitrary. So we end up with the integral of du, again, a very famous form, a squared plus u squared equals 1 over a inverse tangent u over a plus a constant. So I know when you started doing calculus 1 and you got to integrals, you said, boy, this does seem kind of, arbitrary. We're just throwing these constants around, but the mean value theorem requires this. So when you think about differentials or derivatives and integrals being inverses of each other, they essentially are. It's just you've got that pesky constant hanging around in one of the inverse equations. So again, remember that formulas or functions with the same derivative must differ by a constant. That's the reason you have this arbitrary constant here. And it's not just something that someone made up. And you know this, but just remember that. So now, of course, we have a nice formula like the inverse sine form. This one's a little bit easier, no radical, but remember with the inverse tangent of u over a, we have the coefficient of 1 over a. So just don't forget that. So what I would like you to do when you work on these problems is write these formulas down over and over. Write them down to where you could basically teach them to a friend. That way you'll have a good feel for how to use them. Now, what I want to do is go ahead and get the formulation for the inverse secant because it's a little bit more complicated. And then, of course, on Wednesday, we can do a lot more examples with integrals to give you some more practice. And then, of course, after that, we'll start talking about area bounded by curves. So number 3 here is the inverse secant. And we're thinking, well, did Professor Ron leave the worst one for last? And yes, ladies and gentlemen, I did. I'm trying to get you ready. A little bit more work involved, not a lot. So we have y equals inverse secant. This is why we have to pay attention to how we define, and I will use the definition that Dr. Larson uses in our textbook. So y is equal to the inverse secant of x if and only if. Again, we'll apply secant to both sides. X, you're thinking we're doing the same thing again. And you know what? That's good. Because after today's lecture, you'll be able to do these derivations for your friends. Now, what does this mean? If we look at this and we think about this, we've got x's and y's running around the place. Now, where do the x's live? Now, think about the process of making the secant function 1-to-1. This is going to give us x in absolute value greater than or equal to 1. Remember, the function's going to have branches that go off into the positive x direction, into the negative x direction, but they're horizontal asymptotes because the secant branch had vertical asymptotes. So y lives, this is kind of like the inverse tangent, but a little bit different. Y lives between 0 and pi over 2, but you got that issue at pi over 2, so you exclude that. So it's the interval basically from 0 to pi, but we're leaving out pi over 2. Okay, so again, I saved this for last because it's a little bit more complicated, but only complicated in that when we actually think about describing the inverse secant, there's another method for describing it that's not like this. What's nice about this particular formula, it does introduce an absolute value sign in the derivative formula, but it preserves the following equation. That is, it preserves the reciprocal identity, preserves the following. Lots of students say, man, I don't like that absolute value, Professor Ron, but this is good. That is, secant, inverse secant of x will now be written as the inverse cosine of 1 over x. So this is a very, very nice identity that our particular definition of inverse secant preserves. So Dr. Larson even talks about this in the textbook, and it is good. It's worth it. It's worth it. So remember, when you look here and here, you see that this is preserved. So this is useful. I'll just say useful identity. And sometimes it's difficult to move from one part of a problem to the next because you're struggling with this. So in our Calculus 2 class, we will be able to use this identity. Now, of course, we want to differentiate implicitly, so I'll type that out. So differentiate implicitly. I know I keep typing the same thing, but I want you to be sure that you understand this. So like I say again, the technique doesn't change, it's just the particular objects change. So again, we go right up here. Sorry, I want that. We go right up here. To this equation. Oh, we got 23 people in the class. That's wonderful. Plus 4 more. Excellent. Okay, so now when we look at this, let's differentiate with respect to x. So we're going to get 1. And now what's the derivative of secant? Remember, that's secant tangent. So we get secant y times tangent y. So if you think about the lecture today, times what, dy dx, I put a little times there because we got 2 factors. I don't want you to think I'm being sloppy, but just to kind of note that additional factor. Notice, what have we used today? We've used Calculus 1 and trigonometry. So we really haven't learned any new math. We've just learned some ways to put together ideas that we already know. So good for us that we have enough knowledge to be able to do this. Now, if and only if. Notice, we now want to solve for dy dx. And when we're living in these particular areas here, we don't have any problem with division by 0. So we can do that. So now dy dx, we'll have to do a little bit more work, but not much, will now equal 1 divided by secant y times tangent y. Now, what we can notice here is the secant y is just x. We see that right there, so we're done with that. But the tangent y, we're going to need to use our Pythagorean identities. Now, this is where we have to be a little bit more careful, because now that things will change up a little bit. Now note, this will equal, if you will. Now, when we replace tangent with secant squared minus 1 radical. Just let me just go ahead and write up here. Remember, tangent squared y will equal secant squared minus 1. So that's the Pythagorean identity. But notice, in this particular interval where the y lives, the tangent is positive. But in this particular interval, the tangent is negative. So we're going to have a function in pieces. That's where the absolute value is going to come in. So now we'll do our replacement. This is why it's very important to remember where the x's and the y's live. If not, we're just making it up. So we're going to have 1. So we have secant y, again, this case, which is just x. And again, secant squared minus 1, that's x squared minus 1. And for this is x greater than 1. Of course, we can't divide by 0, so we have to kick out the 1. And now, for the other side, we get the negative. But x is going to be negative, and that will absorb it. That's where the absolute value is going to come in. So now remember, for y's living here, the tangent is negative. So we'll have a negative sign, which I'm just going to go ahead and pull out to the side here. So we're going to have the negative x radical x squared minus 1. And this is when x is less than negative 1. But now notice, when x is less than negative 1, we have a negative of x. That's the absolute value of x. The additive inverse of x here is the absolute value. So now we can combine these two pieces with the absolute value function. So notice, let me say this one more time. This is important. X here is less than 0. So the negative or additive inverse of x is positive. So this part right here is greater than 0. So what we can see now is, even though this was a little bit difficult to deal with, when it comes to working with the inverse secant, we can now say this is just 1 divided by the absolute value of x times the square root of x squared minus 1. And so now let's just go ahead and fill this in. Now this took a little bit more time, but ladies and gentlemen, the only issue was dealing with this. Otherwise, we did exactly the same computation, no different whatsoever. So now this is actually the derivative of the inverse secant. So you're thinking, okay, well, with this definition that Dr. Larson uses for the inverse secant, we do preserve the reciprocal identity, but we do incur the absolute value in the formulation for the derivative. But now notice that this is always positive, and so that our function derivative is increasing. So that gives us, maybe another plus there. So this is the derivative of the inverse secant. So there's our formulation. Of course, now we're going to extend by the chain rule. So let's go ahead and do that. So here, let's go ahead and do some text. Suppose u is a differentiable function of x, and let's do a chain rule extension. So this implies that now the derivative with respect to x, we're just going to tack on the du dx, inverse secant. What's nice about these calculations is that By knowing these, we preserve a little bit of our knowledge of pre-cal, because in chapter 7, we do a lot of non-calculus or trig stuff. And so we need to make sure we've got this under our belt. So this will just be 1 divided by, now replace x with u, absolute value of u, square root u squared minus 1 du dx. So we have a very, very, very elegant formula that's called the chain rule extension. Now, you're thinking, well, how can we develop this into an integral formula? So now what we're going to do is, this implies, if we just now want to move the absolute value into the argument, this implies that the integral du over u times the square root of u squared minus 1. Again, this isn't extended with the a's. We're going to do that. Will now just be flipping the absolute value just to take a particular case here. This will just be the inverse secant of the absolute value of u plus a constant. Sometimes textbooks are not very good about motivating why these formulas are actually true. They say, well, just verify this. But again, you have to use your pre-calculus to understand this. That's all it is. And so now what we want to do, that is, with this integral formula, we want to extend by an a. So again, I'll just write this out. Suppose a is positive. Now, if we think about the previous slide, we need the following. So replace u with u over a. I mean, this is a common technique in mathematics and in science. We create formulas that help us get to the finish line. So with u over a, just like we've done before, where, again, we don't want to divide by 0, the absolute value of u over a is less than 1. So now we can go ahead and fill in the left-hand side, and we're going to get just like what we had for the inverse tangent form. So this implies the following. I like what we're doing today. It's getting us all back into our trig. It's making us think mathematically, just using a lot of college algebra. So now we have the integral, the differential of u over a. Remember that 1 over a is just going to come out using our formulas for differentials. And here we have u over a. And I'll use brackets here. So u replaced with u over a will give us u squared divided by a squared minus 1 to the 1/2 power. So again, when we think about this, there's not a whole lot of calculus going on. Once we take a derivative, then all we're doing is algebra, just to make the formulas look user-friendly. So now the 1 over a here, this is just 1 over a times the differential of u, so we can factor that. I'm just going to leave everything else downstairs for now. And if you like, well, maybe we'll just go ahead and do this. Notice this is a u over a, so we have 1 over a, so that's just a. So we can just put an a right there to get rid of that. So this is du, and we're just left with u now, because 1 over a we just put right there. And let's get a common denominator inside the radical. Again, very simple algebra. You know, it's amazing that calculus requires us to do algebra 1 and algebra 2. U squared minus a squared. So notice this mimics all of the examples I've done with the inverse trig functions. We're doing the same thing here. So now if you look at this, the a over a, that's just a 1. And now here we have the square root of a squared, which is just the absolute value of a, which is a since a is positive. So again, this is 1 over a, which is just a. Notice here, these absorb, but we're left with a 1 over a. So that gives us du u square root u squared minus a squared. So we keep using this. Let me write this out again. 1 over a equals a. You know, that's amazing. That's saying, what do you multiply 1 over a by to get 1? A. That's basically what we're saying. Now this equals, we'll go ahead and say, all right, well, let's just put this down here. This equals, using our formula here, the inverse secant. I don't want to push on the shortcut keys, these little pins, u over a, and I've got my little absolute value here. Let me do this. I don't need the a to be in the absolute value, so I'll just do this. I'll leave it outside. You can certainly put it in, but you don't need to. And I'm, again, like we did before, I'm going to call this C1. So equivalently, we can divide by a here. So the integral of du divided by u times the square root of u squared minus a squared will now be 1 over a. So now these formulas are plagued by the 1 over a. The inverse tangent form, the inverse secant form had the 1 over a. The inverse sine form, no 1 over a. So don't get tripped up by that. Write these formulas down so you know these. Always write the formulas down. Remind yourself of what we've done. Familiarity through, just practice. Again, you can slap the absolute value on the entire function, or you can write it that way. And then, of course, now we'll say 1 over a times C1, just like we did before. We're just going to call that C. So now we have our next standard formula. So now we have 3 standard formulas that we didn't know about previously, that it can be actually quite useful. Now what I want to do, and we've done some good work here today, lots of good computations. I've got some examples that I want to do from your WebAssign. Now, one thing that we're going to notice here, and this is very important, when it comes to working these types of examples, it does not matter how you approach it, as long as your approach is one that works out consistently with the formulations. So let's look at a simple example. Let's go on to the next page. So here's an example.
The next.
Yes.
WebAssign?
Yes. Yeah, this will be a WebAssign example. So let's see here. Let me just go ahead and show you this. Here we go. Do this. Let me see if I can get out of this. Oh, here we go. So I'll just go ahead and write this one. So we have something that looks like this. We'll have du or dx. Go ahead and write dx this time. And say we have x, and then we have the square root of, in this case, we'll say 2x squared minus 9. Okay? Now, what I did here is I've tried to start out with a problem that already has the basics set up. And when we look at this, we're thinking, well, this looks like inverse secant form. We don't, next class, we'll do some more elaborate algebra with some completing the squaring things. So now we look at this and say, okay, well, let's see, this looks like inverse secant form. So let's do some manipulation. Note here, u will now be, we want to write this as a square root of 2x, because when we square that, we get 2x squared, and a is just 3. So let's go ahead and fill that in. So we get, and I'll use brackets now since it makes it a little bit easier. This will be square root 2 x squared minus 3 squared. I'm, again, just mimicking the formula to the 1/2. Now notice here, we need a u here. We have an x, so what we're going to do is put in the square root of 2 and then pay for it. So here we'll have the square root of 2x and then pay for it here. Now notice what I've done here. When you look, and we can go ahead and write a little extra here, du, take the differential. Lots of times, ladies and gentlemen, we're not going to convert to another variable because we've got too many tasks at hand and we're just going to look for table ready. But for right now, we can go ahead and write it out. So when you take the differential here, du is just the square root of 2 dx. So now look, this is table ready. Notice right here, and I'll write this out, this is du here. So this part here, this is really so easy. I want you to enjoy this. This is du. This right here, what's the square root of 2 times x? That's u, isn't it? This equals u. This is what? U squared. And this is a squared. So sometimes you just need to do a problem that's pretty straightforward, but then you have to do some algebraic manipulation. So if you like, and I normally won't do this because what we say is this is table ready. Table ready, in the sense that we're ready to use our integral formula. Now, what might be interesting here is to go ahead and just write in the new variables. Now, normally I won't do this, but I know I want everybody on the same page and comfortable with this. So this is really just what? Du u u squared minus a squared. That's exactly our formula for the inverse secant formulation that we just derived. And so you don't have to do this. I'm basically just showing you that at this point we're done. So what does the formula say? Let's just go ahead and write down the formula, then we'll fill it in. This is 1 over a inverse secant absolute value of u divided by a plus a constant. So let's just fill it in. So these last 2 steps, I'm simply adding to make you comfortable with what we've done, but you don't have to usually include these. Just play it by ear. Do what you feel is most comfortable for the level of understanding that you have, and then you can eventually leave out more steps. So this will just be, what's A? That's 3. So 1/3. And then this fill it in secant. Most students will say, well, why don't we have a square root of 2 out front? Well, ladies and gentlemen, we doctored it. And so we have exactly what we need. So this is one of these problems where you do have to pay attention to the table ready form. So now we'll have the absolute value, square root 2 times x. Of course, you can leave the square root of 2 outside the absolute value if you want. We'll rewrite that. And then A is 3 plus a constant. Now, of course, WebAssign would be fine with this. Now, you can factor the root 2 if you wanted, and you can just write this as 1/3 inverse secant square root 2 over 3 absolute value of x plus a constant. Now, again, remember when you're typing your answers and your responses in WebAssign, I give you several attempts in your homework, but when you do your tests and your quizzes, you only have one attempt. I can always see a careless typo. That's going to happen. And I will always look at your work and assign you credit where you have made a careless typo. That's going to happen. But just make sure that when you write and you type what you're doing in WebAssign, that you are actually typing what you intend. And you may have to look at it 2 or 3 times. So now what we see is the only additional thing that we have to do with these types of problems is to look for some more interesting types of examples. Now what I have here, I want to go ahead and do some more examples. We can do some more integrals here, and I've got some examples where we complete the square, so we're going to be ahead of the game. So now what you're seeing is, let me just write here, and I'll just type this. We have 3 new integral formulas that we have derived using the inverse trigonometric functions. First time I've typed that out, trigonometric functions. Now, what I want to say, and this is what you can read, is that the remaining inverse trig functions derivatives just differ by a negative sign. So I want to say this, so you'll have this. That is, observe. I'm not gonna write all of this out. I'll just do one example here, and you can fill in the rest as you read your book. Observe. And I've got a little trig exercise I want to do too. Observe that the derivative of the inverse cosine, we didn't just leave this out because we're being lazy, ladies and gentlemen. We leave this out because the negative signs are the only difference. And so the literature just says, okay, you can leave it out. So if I say the derivative of the inverse cosine of a differentiable function u, this is just the negative of the formula for the inverse sine. So this will be the negative of 1 over the square root of 1 minus u squared du dx. So we didn't get lazy here. We didn't just say, oh, well, you know, this is what's going on. You know, why didn't we do this? This is the same. It's same for inverse cotangent and inverse cosecant. So I'll just say same for the remaining 2. And we'll just go ahead and write those out. So the derivative So we didn't leave these out because we were just being careless. The derivative of the inverse cotangent, and if you run up against these, you'll just know them of u, will now just be the negative of the formula for the inverse tangent. Amazing, right? Not really. So you're thinking we could have just started with these formulas and done the same for inverse sine, inverse tangent, and inverse secant, but the formulas that we derived are by convention the most useful and the most used. And then the derivative of the inverse cosecant. So this is really saving you a lot of time. Will be the negative of the formula that we have for inverse secant. So this is the absolute value of u, square root u squared minus 1 du dx. So like I said before, the focus will be on the ones that we've derived. And I just want you to be familiar, if you come up against these, that you have the formulas already. So again, nothing new here. Now, I've got some examples here that I wrote out. Let me see if I can find them. That really were kind of interesting. And they have to do with yesterday when I was worrying about trying to compile an email list for all my conference hours and having 10 or so students without valid Sanjak emails, I came across this example, and it's actually one that's written up in your WebAssign, but it's masked as a derivative problem. And then when I looked at it, because of course I teach a lot of calculus and I teach a lot of pre-calculus, I thought about the fact that, well, if the student already knows this particular fact, they won't have to do this derivative. And you're thinking, Professor Ron, you don't give us a break, we just work forever. Well, sometimes we have to work to stay ahead. And I'm not going to say that I'm ever going to give you a break or give you lots of breaks. I want you to be focused and just know that Calculus 2 is filled with tremendous amounts of material and no time like the present. So here's some interesting facts. Number one, and this is something from pre-cal, that is for real numbers a and b, a sine x, and you learn this in pre-cal, plus b cosine x. So sometimes we need this pre-cal, and this is a formula we're actually going to use, equals the square root of a squared, excuse me, plus b squared times sine. This is often what you use in differential equations and also in solving trig equations. This will be x plus phi. I learned about this when I was at the University of North Carolina, and we talked about it in trig, but we also used it in our engineering math classes, where, and of course, Dr. Stewart uses this in his pre-calculus book, which is one of the best pre-cal books out there. I use that for my classes, where I wrote this here, tangent of phi, this kind of defines what phi is, equal b over a. So the proof of this is not really very difficult. But if you notice here, this is simply, and I'll go ahead and say a and b are real numbers. So what's important about this is that you notice that we write the sum of two trig functions as a single trig function. That is the sum formula for the sine function. Now, if you took me for pre-cal, you'd use this, but maybe you didn't, and maybe you have seen this, maybe you haven't, but we will use it again in this class. Now, what I want to do is also, so use this, use this formula, use this formula to understand. I'm going to say understand because I'm not going to give you the answer. We're going to understand it because we use the formula. Understand the value of the following. That is inverse sine, inverse sine of x plus inverse cosine of x. Now, of course, this would be where x would have to be contained between what, -1 and 1, using the definition of the inverse sine and the inverse cosine. So there are times when we do need to understand the formulas and the basic attributes of the inverse cosine. We don't forget about it. It's just that the calculus of the inverse cosine is wrapped up in the inverse sine. It's still important though. So now we're thinking, what is this? I mean, why did Professor Ron write this down? What if I had to differentiate this? You're thinking, wouldn't that be 0? And you're exactly right, because we know that the derivative of the inverse cosine is just the negative of that of the inverse sine. So if you see a problem like this, you're done. You don't have to work. You know, and then you're thinking, well, why do we need this, Professor Ron? This is a good way to look at this. So let's just see what the value of this is. This obviously is a constant, but what is the constant? Let's figure it out. So we'll use the same technique we had before. And I think what I used here, I used theta and phi. Let theta be inverse sine of x, and we'll have phi be the inverse cosine of x. Now, equivalently, this will just be x equals, take the sine of both sides, x equals sine theta and I won't write the ampersand this time, it's a little bit easier to write, x equal cosine phi. Now, let's just recall that the inverse sine, this is going back to where we were before, lives between -pi/2 and pi/2. So this is really a pre-cal problem, but it's not an easy one. And the inverse cosine, by definition, lives between 0 and pi. So now basically x equals x. So this just says if and only if sine theta plus, and maybe I should have used another element here for the phi. I kind of cheated. I could have maybe should have used a beta. It doesn't matter. We'll survive. So we have sine phi plus, oh, excuse me. Let me go ahead and go up here. All right, so these have to be equal. Equals cosine phi. But now we're going to write it so it looks like Formula 1. This will be sine theta minus cosine phi equals 0. So now we have A equals 1, excuse me, and B equals -1. So now we can look at this and say, now up here, if you want, we can just use for phi up here, I'll just use a beta. I'm sorry about that. I should have used different notation. So we'll have tangent, just to go ahead and use a different letter, I'll just replace the phi up here with beta. Tangent of beta equals -1. But of course, that's just a principal value for the inverse tangent. So beta would just be what? Inverse tangent of -1, which is -pi/4. Now, when we look at this and we think about what we need to do here, the idea is that, okay, so what does that do for us? Now we can use our identity here to finish off the problem. So equivalently, we'll just replace the sine theta minus cosine theta. So a squared plus b squared, that's going to be square root of 2. So square root of 2. So we're using the right-hand side. Sine of x minus pi/4. This must equal 0. And so now divide by square root of 2, that would just give us 0. 0 divided by the square root of 2. So we have x minus pi/4, take inverse sine of both sides, will equal inverse sine of 0. But we've already done inverse sine of 0, that's 0. So you're thinking, boy, this is a lot of work, Professor Ron, but it gives us exactly what we need to know. So x is equal to pi/4. Now, why does that make sense? Well, of course it makes sense, because now the idea is that when we look at these particular values here, they have to be consistent with the inverse cosine and the inverse sine. So what we can see at this particular juncture is now when we go over here and we think about what's going on, we have a value. That is, now we see that inverse sine of x plus inverse sine of x. Again, I've been sloppy about using different values. This will just be pi/2 for x element of -1 to 1. Therefore, so this is actually a different proof. Therefore, the derivative with respect to x of inverse sine of u, again, u would be a differentiable function of x satisfying these restrictions, plus inverse cosine of u must be 0. So if you're doing a Weber-Sign problem that looks like this, you're done. So this gives an alternate proof. So what I want to say here is that when you think about what we've done and you're thinking about the problems that we've done, it appears that all of this work is basically utilizing what we've already talked about today. So what I want you to do once we finish today, now, of course, I'm still waiting for to check out my Sanjak emails for all my students. That is, I cannot set up conference hours through Blackboard because each meeting is separate for each section. And so I've got to set up conference hours for all of my students. So I'm waiting for some of my paperwork for some of my students to get finished so that they can have a valid email account. If you're already using your Sanjak email account, then it's fine. And so I want that to filter through. So what I'll do for my office hours this week, I'll be available through email and WebAssign messaging. And so as soon as I can compile that list and have a valid list, because if you're not on the list, then you won't get an invitation to the conference hours. So I want to make sure that's complete before we start doing that. So what I want you to do for homework, that is number one, begin, and I can actually type this. Let me just go ahead and type it. So we'll do this. So number one, begin work on WebAssign sections 5.7 and 5.8. 2, study lecture notes and PowerPoints. And 3, review the first practice test. That way you can just see what's going on as far as the types of problems we'll do. Review the first practice test. And what's important here, note the homework, I'll get it right, the homework and quizzes will help prepare you for the semester tests and the final exam. So for right now, I'll probably be using the WebAssign format to test you. And when we have tests, I don't necessarily think I'm going to lecture on that particular day. I'll kind of decide for that when we get to that point. Mainly what I want you to be able to do is that I'll give you a window of a day to complete the test. You won't necessarily have to take it during the class time. But as far as the homework goes for each week, you will complete homework sections each week, and they will be due at the end of that week or the beginning of the next week. And you will also have a quiz when we don't have a semester test that must be completed also. So what I want you to do is organize your work so that you are always consistent and caught up, and work to make sure that you complete all of the topics, and then take advantage of my conference hours to ask me questions to keep, in light of everything that we're doing. So let me just make this comment one more time. If your Sanjak email is fine and it's working, then you don't have anything to worry about. If you are new or you haven't set it up by setting up a password and claimed your account, Sanjak account, please do that, because again, I'm going to try again to check my email listing. As I did it yesterday, there were, I would say, around 10 students that didn't have a valid Sanjak email. So for today, from the syllabus that we have office hours from 11 to 12, and we have office hours from 3 to 4:30. And so for those, I'll be available by email and for the WebAssign messaging. If you're working on a WebAssign problem, you can message me and I'll check my WebAssign messages. So make sure you get set up with your WebAssign. Make sure that you are set up and checking out this course every day. And if your Sanjak email is fine, then you're good to go. This was a good class, and I appreciate your listening. We've got a lot of work to do, so make sure that you take time to study this class every day. I want you all to have a great day. I love math. I have two loves in my life, mathematics and music. And I hope that you have found your love for mathematics because you want to do engineering or mathematics or physics. I'm here to help you. My reputation is that I am challenging, but I want your success as badly as you. I just want you to put in the time and work hard and work consistently. So everybody have a great day, and I look forward to hearing from some of you during the office hours. We'll see you later. I'll just wait for you all to file out. I know who's here. I'll check the report to take the attendance. Thanks, everybody.
Thank you for the class. Have a great day.
Oh, you too.
Thank you.
Thank you.
I know this is an early class. You all are to be commended. I would have never taken a class this early when I was your age.
Hello.
Yes, hello.